Hello, ooh, fluffy hair today. Welcome to Practicalli with me, John Stevenson. Thank you very much for joining me on this chilly morning. Hopefully it's not quite so chilly where you are. So today I'm going to do some more exorcism.io challenges, and there's one specifically called Space Age that we're going to have a look through. It should be fairly quick, so this might be a little bit shorter than normal, but we'll have a little play around with trying to make that function more pure and try and reduce some of the redundancy that the sample code kind of encourages. Okay, website. As usual, it's all everything I'm doing is all on the website. There's another update from what I've been doing for Clojure together, so you can see what I've been doing the last couple of weeks. And the videos, the books, I did some more stuff around kind of accessing documentation via Practicalli, so that you can get the Java and Clojure documentation. Actually, I put that into, oh no, it's in Spacemacs, isn't it? I did some updates on Spacemacs. So if you go in here, you see how to get the documentation for CyderDoc and related functions. So you can use apropos, use JavaDoc as well, and also navigate the source code, which is quite useful if you're doing Java interop, as well as like using comments and even doing some markdown for your readme.md files for your source code repositories. You can do some collapsing as well. Just it's a little bit, it's got some of the features of org mode in that you can collapse headings as well, so you can just focus in on particular parts of the documentation you're writing. Alrighty, let's get back to what we're doing today. Oh, and if you want to reach out to me, then there's these channels, and if you want to support me, then there's these ways as well. Alrighty. Oh, morning to everybody. Thank you for saying hello. Feel free to ask any questions as we go along in the YouTube chat. Let's close that now. So, exorcism. So hopefully you've seen exorcism already. There's lots of different challenges. Here's the Clojure track. And I haven't done that many, but I've been mentoring, as I've been mentoring people on this, I've been doing more of the exercises so I can mentor them properly. And I kind of haven't really done it in any particular order. I've just chosen ones that actually sound quite interesting and skip ones that sound quite fiddly. So the run length encoding is a bit fiddly. Armstrong numbers was fairly okay. Bob was okay once you understand all the rules, but that's probably the biggest challenge with that one. So we're going to have a look at Space Age, which is this one here. It says it's easy, which it was fairly easy. Oh, don't look at my solution yet. Yeah, even I kind of asked for a mentor kind of improvement as well. And we'll cover like there's an interesting solution there with some at first gnarly looking code, but it's kind of an interesting approach. But we'll have a look at that as well. But essentially, you've got if you're given age in seconds, you can calculate how old somebody would be on a particular planet. And so these are all kind of relative to like kind of Earth's orbital rotation. So in case you weren't aware, the Earth rotates around the Sun after like 365.25 days. And then all the other planets have slightly different orbits. And these numbers are relative to the kind of the Earth years. So there's 365 days. It takes the Earth to rotate, and then these are all kind of fractions of that orbit with respect to what all the other planets do. And so you're asking to find out the age given a number of seconds. You need to calculate how many years somebody's been on a planet. So let's have a look at the code. Oh, that's not the code. That's some hacky thing I was doing last night that didn't work. Let's see, space. I'm going to go to exorcism. And oh, that's word count. We'll do word count at some point. That's quite a nice, easy one. Oops. Let's do space age design journal. There we go. So the code is up on GitHub, and oops, let's make that a bit bigger. There we go. Along with this design journal, which is how we started to work out how to solve the problem. And I'm just using these rich comment blocks just to make it clear that you can just have to come here and evaluate each of these expressions individually. So I thought with how to start by thinking about how to represent the data, and as it's basically just a collection of values, then I was going to keep to the same model and just basically use a hash map just to define, it's like key value pairs, the key being the planet and the value being the kind of the orbital period relative to the Earth orbital period, which kind of made it tricky. If you stick to that, I think it adds a little bit extra duplication of code. You could actually just work out the Earth day, like the days for each of those as well, which I don't think I did, but it might be an interesting approach. But let's see what we did. So I can define this hash map and give it a name, so I don't have to kind of keep typing it in all the time. And obviously to get hours in a year, like we divide by 24, or sorry, times by 24. So we take the days in a year and times it by 24, and we get that's how many hours they are in a year, and then times that by 60, and we get that figure, and then times it by 60 again for seconds, and we get a very big number. And Clojure is putting this kind of extension on here as well, although there's only like a couple extra numbers. So I think this is a slightly different type. So these types are still like the integer types. So whoops, I can't type. There we go. So that's still like a double, so it's a large integer, well, a large floating point. And then once you get over a certain size, oh, that's still a double. Okay, it's just showing it in this E notation. Eventually, it'll be have to have like a big. I think it's a big int. I think it's a big double as well, or something equivalent to that. So we can work out like years to second just by multiplying these together, and then with the orbital period, we can then get the kind of the answer that we actually want. So we've got here we're just using a partial function. So it's basically saying multiply hours, minutes, and seconds with something else when you get it. So we pass the Earth orbital period into there, and we get years to seconds specifically for Earth, which is the same value as was up here. So that's another approach we can take. Or we can just write a function which takes in an orbital year and does the calculation as well. And then we can get, oh, did I change that, didn't I? Oopsie. There we go. So that gives the same effect. So there's quite a few different ways to do that. So I went with the function for now. And so it's easy enough to work out if we're given a number of seconds, then we can work out that kind of the time in years, the time spent on that planet in years, by dividing the seconds by the rest of the calculation. And so if we get seconds, if we get like a billion seconds, then yeah, we're still getting the same results. So that's working okay. So we've got the years. It's got a very long number on there as well. So we could format it. If we format it, then it's going to return a string. If we jump to the tests, go to the test and look at space age, then actually we see that the tests are doing something interesting. They all use this rounds to function. So we're passing in the seconds that we're spending on the planet, and this is the kind of result we're comparing it against. And so we're saying that if we round both of these up, they should be equal, basically. So we use this maths round, which is the Java function. So if we could do comma h and look at the Java doc for that, which then opens a little browser. So it basically just uses the Oracle documentation on their website, and this is the math round method. It just tells you what it does. So basically returns the closest int to the argument with ties rounding to positive infinity. So it's basically going to round up if it's over 5, I think, as well. But what it's doing is it's comparing integers. So it's kind of, so what we're doing is basically timesing each value by 100, which instead of being a two-place decimal figure like 31.69, this becomes 3,169, and we do the same thing for the result space urge. So therefore we're actually comparing two rounded up integers, and then if they're the same, then that works. So dealing with like floating point comparison can be a bit tricky, especially using some of the other maths functions like the numerical tower. You sometimes get to a point where you're not actually being able to compare stuff together because it's not producing an exact enough number. So this was an interesting way to get around that issue, just by making everything effectively an integer and comparing like 3,169 against hopefully 3,169, instead of comparing 31.69 against 31.6 blah 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 blah. Hopefully that makes sense. And then these are all just passing in seconds and doing rounds up as well. So there is a slight difference in the way it works, which adds a little bit of complexity to the final solution, but because we've got age in Earth years and then age in Mercury years, but it's not too difficult. But the upshot is we don't actually need this format anymore. First of all, it's returning a string, so we'd have to convert that back to a number, which is a bit fiddly. So we can just have this this decimal point number. That's all we need to return, which is handy. Yeah, because when we do this, when we compare the value we get back from here, which is a slightly different number, which is 31.688. But once we multiply and round that up, then we get 31.69. So they therefore equal. And if we So when we're dividing values, then we might actually get a ratio. So we might, if we divide 22 by 7, in most languages we're going to get a decimal figure, but in Clojure it's got a ratio type, so it's actually returning the value 22 over 7, which is very useful if you don't want to lose precision. And but sometimes you actually want to force it into a decimal value, especially when you know kind of the number of decimal places you want. So we do know that when we get to the test, so that's why they're kind of multiplying by 100.0 is basically to force any ratio type into a decimal figure rather than a ratio value. Because if you multiply 100 as an integer with a ratio, you get a ratio. But if you then multiply it by a decimal figure, then it knows it's got some precision. So it knows it has some context that you're timesing it by a decimal figure. So then it wants to return like a decimal figure because it's more specific context than the general ratio. So therefore, it's returning the decimal value. So we don't really need to do any conversion of the results, so that makes the solution a little bit simpler. So we can just basically have kind of general form of we're taking in seconds, and for the Earth use case, then we're just timesing by the Earth orbital period, hours, minutes, seconds, and we get our result. And that worked. That made the first test pass. First test being specifically age in Earth years. So that works okay. But we've got the other planets. And these planets are not expressing. So to me, the more I think about it, this is kind of bad data, or not as useful data, because it's basically one piece of all the other pieces of data rely on this piece of data, which makes it a bit tricky if you're just putting it into a hash map. There's no way to kind of refer to Earth there just by using a hash map. We can use a let statement, but which I think I've done later on. So all these are relative, so they aren't really kind of it doesn't take 1.8 days for Mars to orbit the Sun. That would be a really fast moving Mars. We'd never be able to land on it if it was moving that fast. And so we have to kind of come up with a calculation for Earth, and then a slightly separate one for all the other planets. So for the other planets, then we've got Mercury, so this is pretty much kind of like to solve the second test. We're taking in seconds, just like before, and dividing those seconds, but this time, instead of just with the Earth orbital period, we're multiplying that first by Mercury's relative orbital period. So it's basically going to take this value and multiply it by the 365 days, and then we get the number of days for Mercury. Of course, we could actually just go in and create a new hash. We create a new hash map with all the updated values. Actually, that might be quite a nice thing to do. But this works. This is fairly straightforward. So we've just using the relative orbital period of Mercury, and this generates the results that Mercury was looking for, and then that passes the Mercury test. And then pretty much the same thing works for all the other planets. And yeah, so that's mostly done. So this was a fairly simple one in terms of understanding what it needs to do. There's a few extra things I did to refactor the design. So one of the things we're doing here when we're kind of calling on Mercury, then we're pulling in. We're basically using Earth orbit, so like orbit period here, this hash map. We're not actually passing that as an argument. We're just taking seconds as an argument. That's kind of the constraint we have with the tests. We'd have to rewrite all the tests, and then I'm not sure if it would work with exorcism anymore. Actually, I don't know. Does exorcism actually run the tests? That's a good question. So if you're going to change the solution, you'd have to change all the tests, which I have done. We'll cover in a moment. So yes, so we got the original one on seconds, and then what I did was, I thought, well, ideally, if we wanted to have a pure function, we'd pass in the orbits, so that's the hash map, the specific planets that we want to find out the years. Yeah, I don't think it does. Actually, thinking about it, I don't think it does. I'm too used to using for Clojure, which does run the tests. So I think you could actually submit whatever you wanted in there. I think if you were going to submit an updated kind of namespace with different function signatures, then you should like redo all the tests as well, so that you've got tests that pass it. That just helps that helps people see that you can run tests against it. So we've got orbits, planets, and seconds, so all we're doing is just basically changing the signature of the function call. The rest of it's the same, but that does make it pure. We're giving it all the arguments that it needs. We're not using any shared resource. It's not a huge thing in this challenge because we're defining the map. We're basically hard coding the map into the code. But if we were using that hash map within inside an atom, for example, then something else could go and change that while we were running this function. And so we wouldn't know for definite what the data was that we'd passed at any particular time because we're not passing in a specific argument. So if this was long running or had like threads or futures in there, then potentially there's room for complexity in there, which we prefer not to have complexity. But this works nicely, and it works the same. We get the same results, and we could even just refactor the name, make it just years and all bit. So this would be a nice kind of generic function that we can use for all of the planets. And then what else did we do? Oh yeah, so I did think about refactoring the orbital values just to be a single value. That would get rid of some of the specific values in here, because we get a lot of duplication. We'd have if we just had on Mercury and on Venus and on Neptune, then we'd get this defen repeated over and over again for each planet. This approach does allow us to kind of do a more generic approach, although we still need to figure out how to get that to work for Earth. One of the other thoughts was, well, we're putting in these values, these 24, 60, 60. We're not really adding, we're kind of adding that over and over again if we do each individual defen. Let's show. So we go to space age. Yeah, that one there. Yeah. Yeah. So if we, so this is this kind of solution we got so far. This is the one I've got. This is one I first submitted, and you can see we've got the on Mercury and on Venus because we've got tests for each of these functions. So if we change those functions, then we have to change the tests again. And as this is supposed to be an easy challenge, then it doesn't kind of make sense to rewrite all the tests. It doesn't say anything about that in the description. But we get a lot of duplication. So these are basically the same function over and over again, and the only difference is we're passing in, well, we're not passing in, we're using a different planet for each one. But that makes it nice and simple. I mean, it's easy enough to read, very easy to follow. And we know there's only 8 planets on there because Pluto is a Kuiper belt object these days. And it's unlikely that we're going to get a lot more planets all of a sudden. So it's within the context of what we're trying to do, it's fine. But we get a lot of duplication. So I did think that we could put the calculations inside the hash map, but then this just adds even more duplication to it, and so that wasn't. I don't think that's a nice approach. Although if we just have the actual, if we replaced all these with the actual values of these calculations, then that would simplify that. So we could have a function that just returns the relative values, which returns a hash map, and then we use that hash map with a single function to calculate what's relative. That would be quite nice. Where do we get to? Oh yes. So if we've got that, if we do have this, then we can just basically use the relative objects to divide Mercury, and so it makes our functions a lot simpler. And we get the same results there as well. And so we could, and again, we could just have a generic years. We pass in the relative objects, orbits, planets, and seconds, and that does make the algorithms of each function really, really simple. But then we got the complexity, or just the mess of figures there, which is okay. It's data. It's fairly easy as long as we kind of describe in here what the data structure is. Then that's okay. We could even put a spec around that as well. So we do a Clojure spec to define what the shape of that should look like. Although again, we're going to have to we might need to put in, so we could put in a 1 in for Earth as like the relative value, because we've times something by 1, it's still going to be the same value. So we times 365.25 by 1, it's still 365. So that way we get we get unified structure for this, and we could even put that into kind of a map as well if we wanted to. And then I did think about just using a let to get rid of some of that, but then you've still got lots of duplication. It just looks a bit more meaningful in terms of what the values actually mean. And that still works the same way. But then I decided to just go back to the original one because I'm adding more to the scope of the project than it defines. So just to simplify things back again, just drop back to the standard data I started with, and then we can, it talks about duration, so I've changed seconds into duration to give it a bit more context. So how long you spent on the planet itself, and its relative orbits, and then we can take the duration, the seconds spent, and calculate it. Oh yeah, and I've got I did this seconds to days just to take out the this 24 by 60 by 60. So I've basically just abstracted that part of the calculation away to seconds to day, just to help us like tidy up the code a little bit. And so I've got, so you can either do just the calculation, or I've made it more expressive here just by using a let. So now you can see hours is 24, minutes is seconds, and minutes is 60, and seconds is 60. So this version is just really for adding a bit more clarity to the code. So basically self-describing itself. So the question from the audience: so confused about the this data. So what are the units of these data? So these are, so Earth rotates the sun in the solar system. It takes it 365 days. And then, yes, all the other values are relative to the Earth. So that does add a little bit extra confusion. So it's so Jupiter takes a lot longer to rotate the sun than Jupiter. So if you multiply 365 days by 11.82, you get the number of days it takes for Jupiter to orbit the sun. And the same thing here. So Mars is a little bit slower to orbit the sun than Earth. It just takes 1.8% extra. And Mercury is a lot faster. It goes around at like a quarter. It goes around at like 4 times the speed, more or less, of Earth. Ooh, Neptune's really slow, but then that's got a slightly elliptical kind of orbit, so that takes forever to orbit the Earth. That's interesting. Let's have a look. So I'm just curious how many days that's going to take. So we do, what do I do? Oops. There we go. So if we multiply 365 by what was it? Oh yeah, 164. This will be the amount of days it takes. So 60,000 days to orbit the sun, and that's the Neptune's orbit rate. So that's how long a year lasts. 60,000 days. That's a long year. Ooh. I hope that makes sense. Yeah, so what we could do is just change, if we multiplied all of these values by 365.25, then we'd have the days of that, and we could actually drop this calculation from here. We'd actually get rid of this calculation, and we could just use Jupiter orbital period, which in hindsight seems to be a lot more sensible. I always learn things by explaining things to other people that I've missed when I was doing them. So with these values back, if we didn't do that with these values back, then we've got on Mercury, and so we can just do this for just times the Earth orbital period each time, which works for everything but Earth. Then what to do here? Oh yeah, then just make it a pure function again, which I think we've already covered. So I'm going to skip that. Oh yeah, I'll go that twice. So what it could do, so rather than So we could actually just have single figures in here, and then it would make a lot of things simpler. So we could actually just put this calculation in here as well. So if I do comma E, I think it's W. There we go. Oh no. Oh, I have to do that there. Yeah, if I did that for all of these, I could like replace the values. Oops. W. So I'm just basically evaluating and replacing the results with the evaluation. So replacing the expression with the evaluation, which is just a command in Cider. So this is just a Cider eval last s expression and replace it with the value that returns. So then if we did this, then we could actually just drop the calculation completely. Oops, missed. I missed. There we go. And then you could just have this generic function in here of years, and that would work actually. That simplifies the whole thing really nicely. So it kind of shows that if you've got good data, then your algorithms tend to be a lot easier. Your functions tend to be a lot easier to define. I think I forgot that in the rush to get this done last night. But yes, so that's an important point. So if we actually have this as our hash map, then we can almost, well, we can replace all of the on Mercury, on Venus and stuff like that, so with just seconds divided by this value. And then all you need to decide is just how to actually, whether to hard code this or just to generate this as well. Did I already do that? I think I skipped back too far on the one, or I think I might have cut and pasted something too much. Where do we go? Oh yes. So I think what I finally did was, if I was going to do this outside of the context of the tests, I create like an age on planets, and if we didn't use if we didn't have the calculations in the hash map, then we could just put an if statement in, check to see if there's the planet Earth, see if the planet is Earth, and if it is, then we'll do just Earth relative orbits, and if it's a planet, then we can do we just need to times the Earth relative orbit by the planet relative orbit. But if we use the updated hash map, we can actually just simplify this by using, I'm going to do space K raise, which just raises that expression to the level above, which basically just means I don't need the if statement anymore, and I don't need that anymore. Actually, space K raise that one, and I don't need, oh, I can unwrap that, can I? And then I don't need that either. Boop. And it just makes that really simple. Oh, that's quite nice. So we just have this, oh, I don't know where I've lost it now. So yeah, so we just have this function age on planets, and that would take care of all the planets with, if we'd updated that hash map with the specific values. Let's see, space tab. So there's this solution that works for the test that we get with exorcism, and then I did this pure version, so I just created a separate namespace, and we've got seconds in days, Earth relative orbits, And then we've got this if statement basically saying if it's Earth, then just do it specifically for Earth, and if it's not Earth, then do the calculation respective to the relative orbits of the planets. So basically multiplying these by 365. But then we could just generate a new hash map, just have a function that generates a new hash map, and then use that function when we call age on planet, and that would simplify. We could get rid of this. Design journal. Where is that? That's not that one. There. Where's he on? Pure. There we go. So if we had this instead, relative orbits, then we could just have age on planet. Boom. And we could get rid of raise. We don't need Earth anymore. Don't need that anymore. Oh, we do need the brackets around there, don't we? Because we're basically getting planets from relative orbits. So planet's a keyword, so we can use the keyword as a function to look up the value that's related here. So if it's Earth, then it's going to get the right value. Jupiter, so we don't need any condition in there as well. So we can just do duration. And then we don't need seconds and day because we've already factored that into the change that we've made to these values. And that makes it a lot simpler. I wonder if that should still pass my tests, I think. So we don't need this boom function. And we don't need this function. We don't need that one. Boom. And we can just have a nice simple relative orbits. So if we evaluate that, and then go run our tests. Oh, we're going to failure. Oops. So I've messed up somewhere on the calculations. That's something I'll have to fix. If we boom, just check these were working before. Oops. Yeah, what are we doing? Go away. Yeah. Yeah. More fingers and thumbs again now. Uncomment that. What? Come on. There we go. Evaluate that and that and that. Yeah, it should be okay. Huh. I think I must have stuffed that was working before. What have I done? So what I did was, oops, no, go away. I did rewrite the tests. I'm sure I did. And I rewrote these tests. No, that's not the right one. Pure tests. So rewrite the test just to be pure, and these were basically just using the same approach, except to provide 3 arguments. So I'm passing here age on planets. So the this is kind of the oh, have I got that the wrong way around? That might be why. So passing in the seconds. Oh no, sorry. Yeah, so this is the function we're calling, and this is the relative orbits we're passing in, and this is oh, okay. It's using a different. Is it using a different thing there? Oh no, Earth relative orbits. So we're using Earth relative orbits. That'd be A. We're passing in the Earth, and then the duration it's lasting on. And I'm sure this was working last night. There we go. Something very strange happening there. Okay. I'm sure that's working. I've done something weird to this and I've broken it. Let me see. So if it's Earth, then we divide the duration by... Yeah, that's right. And then we use planets. So that's right. That was working. I'm sure this is working. Live coding. There we go. Not sure why I'm getting wrong numbers now. That's quite annoying. Is that the... Which tests are actually failing here? Oh yeah, space age pure tests. So that's not good. They were passing. I'm going to go check my calculations after the broadcast to see why it's failing, but that's the approach I've taken, and I swear it was working last night. I'll have a look, see at the code, see why it's why the tests are failing. Now it's just not getting the right values for some reason. I've obviously done some calculation wrong. What did I change? I'm going to change the... Oh, I did that, but that's... Shouldn't be using those ones. No, because it's a different name anyway. So maybe something's got cached in the REPL and not uncached. Oh, I don't know. I'll have a look and I'll update it with the fix that I find. But that's kind of made this pure function a lot simpler, and if we use the if we update all the values to be like actually the same thing, it makes the code a lot simpler as well. And yeah, so that would be my preferred approach. I think one other suggestion, if we go back to the website here from the mentor, suggested doing this kind of generative approach to the generating the functions. So you actually, so instead of actually having a set of defins, then actually using a basically like a function, a defin generator. And this is, I apologize, this is really kind of like icky code. This is like it's like macro code rather than kind of standard Clojure. But essentially, it's going to generate a defin using like a symbol name, which is the name of the planet. So it's going to be on, and then the planet name, and then we're going to add a string. So we've got a doc string for that as well. And then it's adding like the calculation in there for that as well. So that is one way to do it. But for me, I find that it's not code I would be rushing to maintain or change at any particular point, but it is an example of using kind of the underlying stuff you can do with Clojure, but it's not kind of the main approach you would do. All right, I'm going to go and see if I can fix those tests. I'm sure it's something simple I've missed off. If you do find a bug, then let me know. But thank you very much for joining me on this session, and we'll do some more challenges and more broadcasts next week. Alrighty, oops. Okay, have a good weekend and see you next time. Thank you. Bye-bye.